Okay, subject I'd like to talk to, it's near and dear to my heart, is a thing that I refer to as Coil-Trol. First of all, it's my patent, okay, which is a reason that I'm near and dear to it, okay. But over the years, I've instrumented more than 1,000 chill water plants, okay? And I put chilled water reset in virtually every one of them, okay? And without exception, the reset schedule that I thought that I could maintain in the building was a lot more aggressive than what the operators felt they could use. And the operators, after a while, they adjust and adjust and adjust the reset schedule so that either it doesn't exist at all, okay, they don't use it, okay. Now, today, virtually every chiller that you buy has a reset schedule that you can implement in it. Some of them work off outside air and whatever, but there's a variety of reasons why chilled water reset doesn't work, that gives you problems that's associated with it. It saves energy by reducing the compressor operating costs, okay? And it does that because the lower the pressure change between the suction and the discharge, the less expensive it is to compress the refrigerant. So, you know, creating 100 tons with a lower delta P and then with a higher delta P across the compressor makes the chiller, can make the chiller more efficient, okay? It reduces excess dehumidification at the coils. That's really the area that the big savings are made, okay? Remember, when you throttle the water through the coils, you still have 40, let's say you're running 45 for the one, another number, or 48, okay? You still have 45-degree water entering the coil. You just have less of it, okay? And the water enters the coil on the leaving air side. So the coldest air comes in contact with the coldest water. So even though you're throttling the water through the coil, you're still doing all of the dehumidification, okay? Whether you need it or you don't, okay? So that's a problem. It stabilizes the air handling unit discharge temperature because the higher the chilled water temperature entering the coil, the more the valve is open, and as a result, you don't, when the controls change, you don't see as much of a change in the discharge temperature. So the temperature leaving the coil tends to stabilize when you have chilled water reset or higher entering chilled water temperature. The problems caused by chilled water reset: as soon as you raise the chilled water temperature, the valve's open and the pump has to pump all that water, okay? So your pumping costs go up with chilled water reset. As your valves start opening up, you can have a problem, far load starvation. In other words, the coil that's at the furthest end of the thing starts suffering because the pressure drop through the piping system is such that they don't have enough delta P at the far ends. Now that could cause you to speed up your chill water pump if you have a VFD on your chill water pump, which most people do today. So you got to speed up that pump and maintain a higher differential. Unfortunately, that differential pressure is maintained all the time. So you wind up with let's say somebody sets it at 45 or something out there, 35, just so that on a hot day you have enough water going to the far ends. The problem with that is every commercial valve that's ever been made that's other than a ball valve or a butterfly valve is designed to operate with maximum 20 to 25 pounds. So if you operate a valve that's been designed for 20 to 25 pounds at 45-pound differential, the valve doesn't close. The spring isn't strong enough to hold the valve against the seat. So the thing starts lifting off of its seat. So even though you think the valve is closed when you put 15 or 9 or 0, whatever it's direct acting, reverse acting, it doesn't close. It's still open, and water is still passing through it. Okay. It also beats the shit out of your seats and your valves. Okay. You wind up in some cases with high humidity in some areas because you don't have enough flow going through the coil, and now the chilled water temperature is high and it can't pull. You don't have that extra capacity left in it to pull it down. So that's some of the problems that are caused by chill water reset. Also, when you have higher flow, you reach the point that the criteria for starting another chiller becomes flow. And that is the case that's everybody talks about, low delta T syndrome and everything in a building, and there's a load of pressure compensated valves that they say will help you with that, so you don't pass too much water through something that's closed and whatever. But and Siemens is selling a flow control package that they charge hundreds of thousands of dollars and put a whole bunch of drives in the system. But in reality, when you raise the chill water temperature, you got to flow more water. And if you flow more water, you're probably going to wind up putting a second chiller on. That's probably not going to happen in a building that has turbines. Okay. Most of these buildings that have turbines, the guys have figured out a way to operate the building on a single machine. Okay. And therefore they run the chilled water temperature down so that they keep the flow down. Okay. And they can't, and they don't want to start. You just don't start another turbine, as you well know. It takes you, an hour to warm everything up, get everything set up to allow you to start a second machine. Okay. And there's various and assorted schemes out there to try to control control chill water and discharge air temperature from relative humidity. I will say confidently that none of them work. Okay, it doesn't make any difference whether you're Johnson, Powers, Honeywell, Foxborough. I don't care who you are. You can't make that work because humidity interacts with temperature. So that's why they call it relative humidity. So when the temperature goes down, the relative humidity goes up. So if you lower your chill water temperature and you get your discharge air temperature down, the relative humidity goes up, which then calls for the chill water to be lower. And so it's an endless cycle. It's a Foo-bird loop. Okay, Foo-bird is defined as a bird that flies in increasingly smaller circles until it flies up its own ass. Okay. So anyway, that you wind up with trying to control from relative humidity as a Foo-bird loop. Okay, so we talked about putting additional chillers on. And the effort that it takes the engineers just to police that whole situation makes it a non-practical way of doing things, okay? So most operators tend to limit it, bypass it, or completely shut off chill water reset. And it's something that, after putting 1,000 of these things and going back and servicing them after the years, it was pretty clear to me that is difficult. The systems I put in were a little bit better because I was doing something close to what this is, but not exactly the same, okay? What the criteria for starting air conditioning last week, okay, when it was 60, 63, 64, okay, but it was dry, okay? And the sun load was pretty heavy, okay? So most of the people started a chiller last week based on the sun load in the tower of the building. Okay, the rest of the building could be satisfied with 62, 63, 64 degree air. Pulling that 100% outside air through the economizer cycle, and then they picked up 1 or 2 degrees across the fan, and for the most part, places were satisfied. The reason that they would need air conditioning is the sun load, typically in the tower, and the relative humidity. As soon as the humidity starts to go up, that's when the load starts hitting the air conditioning. That's when people start getting uncomfortable, okay? And this just goes back to Dr. Carrier and the design of psychometrics when he first invented air conditioning, okay? So what I was looking to do is I was, doing chill water control systems, as I said, more than half of the high-rise office buildings in Manhattan at one time had my chiller controls on them, okay? So I did a pretty good job of marketing that in New York. Subsequent to that, a lot of those chillers have been ripped out. Shows you how old I am. And a lot of the features that I had built into my Thermomizer chiller controls actually came with the new chillers, like PID control and chill water reset and some of that stuff. So I moved on. I worked in the pharmaceutical industry for tight temperature and humidity conditions, and where it's important because the efficacy of the drug is directly proportional to how much medicine's in that capsule, and the amount of medicine that's in that capsule is directly proportional to its weight, and its weight is directly proportional to the relative humidity that you pack the pill at, okay? So it became very, very critical to hold very close temperature and humidity conditions in pharmaceutical manufacturing applications. And at that time, we found out, there's just no way we could control from relative humidity. But we did find that if we controlled from absolute humidity, the grains of moisture in the air, that's an absolute number. So if we could control from grains of moisture, and then assume that the relative humidity was all right if the temperature was between this temperature and that temperature, we could make the rooms very, very comfortable. And in fact, when Kieran over here worked for Wyeth, we did a group of maybe 20 critical temperature and humidity rooms and held the temperature plus or minus tenth of a degree and the humidity plus or minus 0.5%, 24/7, 365. Okay, so it can be done, okay, but it required some different type of control. So what I wanted to do was when I was designing air handling units for a while, I was selling and designing custom air handling units. I learned a whole lot more about the coils, where we're really delivering the really delivering the cooling. So the Coil-Trol is a process where we reduce the excess cooling in the coil, and most of that excess cooling is done either as sensible, because we're resetting the discharge air temperature coming off the coil, and as latent. And those numbers can be anywhere from 15 to 25%, depending on what temperatures you were operating your discharge air on your air handling units to start off with. We came up with a way of reducing the pumping costs by 20 to 40%. We found out that I could increase the delta T across the chill water system to 20 or 25 degrees. Now I can't do that with the chillers, so now my limit is no longer the controlling the coil on the air handling unit. That my limit now becomes what is my chill water plant capable of doing from a delta T standpoint, okay? And by the way, if you slow the flow down through a chiller, you can easily get 17 degrees from it, okay, without going outside the design operating parameters for a chiller, okay? And more importantly, it improves the comfort level because we no longer see cycling in the discharge air temperature. We hold it nice and steady. It increases the lifespan of the chillers because we're not running anywhere near as many chillers as we would have. And it comes down to variable coil flow versus variable temperature control, okay? Right now, all the chill water coils are controlled by varying the flow through the coil. Coil-Trol varies the temperature of the water in the coil. It's chilled water reset to the air handler. But we're doing it on a per air handler basis and a per building zone basis, because the air handlers are done by zones. So I can treat the upper part of the house at it differently than I can from the lower part of the house, which means that a lot of those days where I don't have the sun load and I don't have the humidity load, I can operate at 64 degrees discharge temperature on the air handler, and everybody's happy. Okay? So it becomes, what's the typical, you vary the flow through the coil. We reset the flow in the coil, and we do that by putting a little recirculation pump in the coil. So that recirculation pump recirculates the water in the coil, and we set it up as an injection system. If we need more cooling in the system, we allow more chilled water to enter. If we don't need more cooling, then we bypass more back into the inlet of the coil, okay? One of the problems that I have seen, and it got progressively worse in the 80s, was that the coils started to go into laminar flow. Now, if you're not an engineer, you haven't practiced that for a long time, okay? Laminar flow is when the velocity of the water slows down so much that the water doesn't wash the sides of the tubes. It just goes down the center, and you have this laminar layer between the wall inside of the tube and the wall of the tube. That occurs somewhere between 1.5 and 2 feet per second velocity through the coils. Your typical coil is designed for 3.5, 3 to 3.5. But depending on the coil application, I've seen them as low as 2.7, 2.8. That means that as soon as the velocity gets down to 1.8, let's say, on a coil that's designed at 2.8, I go into laminar flow. It no longer exchanges heat with the air. It does, but at severely decreased rate. So what happens is the coils become less efficient, and the discharge air temperature then starts to shoot up when the coil gets into laminar flow. The discharge starts to shoot up. When it shoots up, the controller automatically goes back and opens up the valve to bring it back to non-laminar flow, to turbulent flow. And that's why on a lot of DDC systems that you see, you got this. And this happens, that cycle might be 10, 15, 20 minutes, okay? It's not like this, it's not happening every 5 seconds, but it's a 10 or 15. Well, what that does is it causes the temperature and humidity in the spaces to go to follow that same curve, okay? Especially the humidity. So that is a problem, and that's the limit. You wind up, the way the operators get around that problem is they set the discharge air temperature down lower. That keeps the valve open longer, okay? But it also causes excess dehumidification and excess sensible heat removed. I'm telling you that most of the coils can't throttle below 40%. And I do a coil selection. I have a computerized coil selection program. I take all the parameters from your coil and I put them into the program, and then I step through the program and I find out what GPM that coil goes into laminar flow. And wherever it goes into laminar flow, I put a pump in that's 20% higher in flow for recirculation. So that pump always keeps that coil out of laminar flow conditions. You always get good heat transfer. You didn't see this problem when you had pneumatic controls. And the reason you didn't see it is you only had proportional only controls, which means you had a throttling range. That means if it was set at 55 and you had a 5-degree throttling range, the discharge air had to go to 52.5 for you to close the valve, and it had to go to 57.5 to fully open the valve. And that was the throttling range of the system, 52.5 to, well, it wound up when the load dropped off and the valve started to close, the discharge temperature would go down, but the valve didn't go necessarily close all the way. So you didn't see the problem, and plus pneumatics are a lot slower than electronics. So you wind up not seeing that problem with laminar flow so much in a pneumatics. But when you have a PI controller, that valve could be 10% open at 5% of load. It could be 10% open at 100% of load. It could be any place in between there. So the problem is something that we created for ourselves when we put DDC control in, and we decided that we wanted to get rid of that proportional offset and make that air handling unit much more efficient. So what we are trying to do is we use the grains of moisture. The problem with changing the discharge air temperature is not losing the humidity control. So we use grains, what I call grains control in the Coil-Trol. I measure the temperature, humidity, I calculate the grains. I know if the grains are 64 or 65 grains per pound of dry air, and my temperature is between 72 and 75, my relative humidity is someplace between 50 and 55, which means my people are comfortable, okay? And I have no interaction between the two control systems. In other words, my two control variables, because one is absolutely the absolute humidity is totally independent of temperature. The design of a cooling coil is always a compromise. You have a thing called sensible heat factor that was designed. That's the ratio of sensible heat to latent heat. That your coils were designed to do that. Unfortunately, we have all reduced our loads in the spaces. We went from T12s to worst condition LEDs, but maybe the T5s or T8s. We reduced the total sensible heat in the spaces. We got rid of all of the CRTs and we put in nice LED monitors on it, okay? Everybody used to have a printer on their desk that stayed cycled on all the time. Now you have a central printing station where if it isn't used in 5 minutes, it cycles itself down, okay? All the sources of sensible heat have disappeared inside the building. When we finally put LEDs in the building, the problem is even gonna get worse, okay? You're gonna have to put reheats in because there's no other way to get around it. So that's something you got to look at when you start looking at replacing the bulbs with LED bulbs. The Coil-Trol will help. It'll help a lot, but I can't solve the problem. I've run the coil selection 88 million ways to the center, and I still can't. I can't make the coil do everything. Okay. But I can because at some point in time I got to worry about the relative humidity, and that's the overriding factor. Okay, the ratio of sensible to latent is interesting. When the coil's at 20% of flow, 50% of the sensible cooling is being satisfied. Okay. A lot of coils, I was saying in the engineers, when we had the energy crisis, first thing they went to do is, hey, we're going to redesign the chill water system to have lower pressure drops. Then our pumps can be smaller and whatever. Well, the only problem with that is they went to the coils and they designed the coils with very low pressure drops, which means very low velocities, which means that some coils can't throttle below 60%. Without going into laminar flow. That's what looks like laminar flow. This is a pictorial of what turbulent flow is. And it literally looks like that inside the coil, okay? This is a performance factor where you can see where at 20% of coil flow, which runs across the bottom, okay, we have 50% of the sensible heat. Now, we just said we can't get to 20% of flow because none of the coils will throttle back that far. To get our latent, okay, at 50, okay, percent of flow, the latent still isn't satisfied. The latent isn't satisfied until you get all the way out to 100%. So this curve is the problem with selecting coils. What we're doing is we're recycling the water and we're continuously changing the entering water temperature into the coil every time I recycle it. So a lot of my coils, when I'm running Coil-Trol, will have an entering chilled water temperature of 57, 58, 59 degrees. If it has an entering temperature of 57 and I get a 10-degree delta T across the coil, that gives me 67 leaving the coil. And it goes back to the chill water plant where I'm making it at 45. Obviously, I can't do that. So I gotta make some adjustments in there. But you know, so one of the adjustments you can make is you can reset the chill water temperature as long as no one coil has a problem with the entering temperature. In other words, they're all satisfying their latent requirement. Then I can operate the chill water temperature up. So I keep on raising the reset schedule. And this is all done within your own automation system, okay? All we're talking about is a pump, a check valve so the water doesn't run the wrong way in the bypass line. Chances are you have a bypass line there already with a valve in it if you had three-way valves in the system, okay? But we're talking about a 2-inch line on a 50, 60,000 CFM air handler. So it's not a big recirculating line. We're talking about fractional horsepower pumps up to maybe 2 horsepower. Okay. Now, it also has some really neat other effects. Okay. There's a picture of a simple way of doing it. Okay. So we measure, you know, return air temperature and humidity. We calculate the grains. Okay, I like to look at the leaving water temperature and the supply water temperature, but that can come from the building automation system. It doesn't make any difference. And then we communicate or send a 4 to 20 milliamp signal to your building automation system. The only thing you need to buy is the pump, the check valve. I advise you to buy a few sensors, but you don't have to. And this little box, the functionality of that little box can be programmed into your building automation system, or we can supply a box that does it, okay? So what happens is this pump either goes this way and recirculates, or it returns it, and this is the controller that's already there coming off your building automation system. That's controlling the discharge air temperature. We're resetting the discharge air temperature. Okay. And while we're still maintaining that we have our temperature and humidity. I'm not doing anything that's different from chill water reset. This is chill water reset. I mean, we all know that chilled water reset works. Okay? It's just, this is getting around the problems associated with chill water reset. Okay. Now, another interesting feature is this pump takes up all of the pressure drop of that load, which means that I only have to maintain 1 or 2 pounds across my chilled water system to keep water circulating it the way I want. Okay. So I wind up that my differential across my chilled water system goes down. Because I'm recirculating a lot of water back to the coil, the amount of flow that's coming from my chiller is dropped by 50, 60%. So my pumping horsepower goes way down back at the chill water plant. I have a lot more chilled water available for all of the other loads, and This is a completely self-balancing system. You don't need VFDs, you don't need pressure compensated valves, which are not cheap, okay? That one pump, which let's say this is a 50,000 CFM air handler and it's a 2 horsepower pump, is around $1,200. Not a lot of money. And this pipe going across is probably a 2-inch piece of copper. So the installed cost of this thing is low, the payback is in months. Not years, in months. Okay? And it solves a lot of your balancing problems. You'll never need a balancer again. Okay? The only problem you can have is if you start running the thing, if you try to creep too much out of it, you could theoretically get the flow down below the minimum flow for the chiller, and then the bypass valve has to open on the chiller, back to the system, so that you're maintaining a minimum flow through the chiller. What we do is we look at your coils. If you don't have the data on your coils, we just take the measurements, physical measurements of the coils, you know, the rows and cross-sectional area, and we run the coils through that coil selection program, so we know where min and max is and where the best place to operate that coil. And then chances are there's probably only 3 different size pumps. You know, one for 10,000 CFM, one for 50,000 CFM, and one for 100,000 CFM. Everything fits in between, okay? And then you could have the cost of a few temperature sensors. That temperature and humidity sensor is critical. That's got to be a good sensor, okay? You can buy a good temperature sensor, and by good I mean they'll guarantee accuracy for 5 years, for $250. Not a lot of money, okay? If you need 20 of them in a building and you have, at $250 a piece, you know, you just spend $5,000 and that's it. That does the whole building.
That starts the circulator pump.
The circulator pump just runs continuously, never shuts off. Winter time, you use it for freeze protection. And you don't have to run your primary chill water pump downstairs, which is, some of these systems, the primary chill water pump is, 200 horsepower, 150 horsepower. Huh?
That's a 250 horsepower pump.
Yeah, and you don't need it if you're continuously. You might have to jog it every once in a while because the water in it's eventually going to get too cold, but you might have to jog it every once in a while or run it at some very reduced level just to keep the water moving through the system, okay? But that will pretty much stop you from freezing. That pump will pretty much stop you from freezing that coil. It's simple, it's not expensive, and it has a great payback. So who's going to give me their wallet and credit card number? Okay.
You wanted money.
Yeah.
You got plenty.
Okay. This is a very simple solution to a very complicated problem that it took me 46 years to figure out in the industry. Okay.
And John, the high delta T,
What's that?
we are only injecting cold water as much as you need.
Yeah, it just
Coming
injects.
back, warm water coming out.
Yeah, this is coming in at 45 or 48 from your plant, right here. And then it's mixing with the water coming back from the coil, which may be 55 or 58. And then so going into the coil, it might be, 56, 54, depends on how much. As that valve opens and lets water out of the system, this then lets cold water into the system. Whatever goes out can come in. But other than that, this is just it's your typical injection system. It's what you have in your secondary system on in your building on your chilled water system. Okay. You can probably do a whole building, you know, if you have 6 air handlers or 8 air handlers, you can probably do the whole building for less than $100,000. Okay, and your payback on it, you're probably on a building, million square foot building, you're probably using $800,000 to $1 million worth of cooling energy, and this, and don't the savings on the chilled water pump is very substantial. If I take a 40% savings on a 250 horsepower pump, that's 100 horsepower. Okay, that's a very running 3,000 hours a year. Okay, 2,500 hours a year. So it's a big number. Okay. Do I have any questions? It's pretty simple. And again, it's chilled water reset. That's all it is, with a little nuance of using that grains control as a usable variable to stop you from getting too much humidity. Okay. By the way, when we talk about running chilled water temperatures and when you start your building up, and I see a lot of people running in the morning, they come up and they try to bring the building down and they try to flywheel the building through the day. And they really don't know if it's working or it isn't working, but they're not getting any complaints, so it works. But reality is there isn't enough BTUs to flywheel in the building. The air is changing, 4 times, 5 times an hour, okay? You can't flywheel that building by you can pull the humidity down, okay? And then as soon as the humidity goes up outside, one thing about humidity, it travels at the speed of sound from one spot to the other, okay? There's a law, Dalton's law of partial pressures, that says that if you have something that's at let's say 1 PSIG here, okay, or 1 PSIA here, and half of that pressure is caused by the moisture, which it isn't. And I have over here a humidity where I got 1 pound of the pressure caused by humidity. The humidity is going to go from here to there at the speed of sound. So it goes right in your discharge damper. Okay? It literally goes right in your discharge damper. Your damper opens up and is discharging air out the side of the building. The humidity is coming upstream from that flow. The pressure is not high enough to overcome the delta pressure of the vapor pressure. Means that when your dampers open up and you say you open your damper 10% or 5%, the humidity comes through there at the speed of sound. If the relative humidity in the building, if the humidity pressure in the building, the vapor pressure in the building is a lot lower than the vapor pressure outside, the vapor from outside is going to come into that building at the speed of sound. You can't beat it. So all you can beat it with is more energy. Let's keep cranking more humidity out. The faster you crank humidity out, the faster it comes in. Okay? So you're shoveling shit against the tide, right? You can't beat it. So all you can want to do is pull your building down to 53 or 54%, or it's even better, grains, okay? If you pull it down to 64 grains, then stop. Don't try to pull it down any further because you're wasting your time. And you're not going to lose your load. As long as that grain doesn't go above 64, you're not going to lose your load. It's not going to happen. It can't happen. Okay? You lose your load because the humidity gets up so high in the building that you can't, all the air that you're trying to introduce to the building can't cool it down. So, it's a mindset until you see it on the screen, until you see the data analytics telling you what happens when I lower that, and he showed one day I do it and one day I don't, or one building I do it in and one building I don't, and you look at the difference, it's going to be all in energy. It's not going to be in comfort. You're not going to make the building one iota more comfortable by pulling those grains down, because as soon as the humidity comes back up outside, it goes in. That's why, you know what, an hour after you shut the building off at night, the interior is the same as the exterior as far as humidity is concerned, okay? Because the moisture comes right in.